Okay, we're heading into the strange world of the quantum for a little while now. I think actually simpler, at least at this level, than we might assume. Let's see how we go. So, first question is, what's the energy of a photon of green light? It's a frequency that's often used for lasers because the materials of the laser make it convenient. 532 nanometers. So we have E equals HF. The energy of a photon is a Planck's constant times the frequency. But we're not given the frequency, we're given the wavelength. So we're given lambda equals 532 nanometers equals 532 by 10 to the minus 9, which is 5.32 by 10 to the minus 7 meters. So working in good old SI units, 5.32 by 10 to the minus 7. So we know the wavelength, but we happen to know that for all electromagnetic radiation, C equals F lambda. It's like the V equals F lambda, but the velocity is the velocity of light, C. So if we want to find the frequency, we can rearrange that. F equals C over lambda equals 3 by 10 to the 8. We know the velocity of light, meters per second, divided by the wavelength, 5.32 by 10 to the minus 7. Just interestingly on the units, meters per second here and meters here, the meters cancel out and the units are F equals 5.65 by 10 to the 14 seconds to the minus 1, but we have the SI unit for seconds to the minus 1, which is hertz. So the frequency is 5.6 by 10 to the 14, not 4, sorry, hertz. So now we can bring this back over into our equation on the left. Planck's constant, 6.63 by 10 to the negative 34 times 5.65 by 10 to the 14. In terms of laying out a problem, do as I say, not as I do. This one's pretty untidy, but I'm trying to do it in a fairly small window. Ends up equaling 3.75 by 10 to the minus 19 joule. Now that's a fairly tiny number, but remember we're talking about a single photon of light. So the energy carried by a single photon of this particular frequency of light, 3.75 by 10 to the minus 19 joule. So that's relatively straightforward. We just needed to know that E equals HF and then know that we could calculate the frequency because we had the wavelength. Okay, so the second one, part 2, is we're asked that if we've got an electron moving in a particular way, what is the uncertainty? So if we use the uncertainty principle, what do we discover for the about the certainty or otherwise with which we can know the position given the momentum? So the uncertainty principle, delta P, the uncertainty in the momentum, times delta X, the uncertainty in the position, must be greater than or equal to h bar on 2. Now h bar is the reduced Planck's constant, which is h on 2 pi. So if we go over here and work on this for a minute, so h, Planck's constant, whoops, sorry, that shouldn't have a bar, h over 2 pi is 6.63 by 10 to the minus 34 over 2 pi equals 1.06 by 10 to the minus 34. Alright, so we've just divided 6 point something by 2 pi, which is about 6 point something, so we've got something close to 1 by 10 to the minus 34, but then that's h bar, and then we're going to divide h bar by 2 as well in this case. So h bar on 2 is just 5.28 by 10 to the minus 35. And the units of h, and therefore h bar, and therefore h bar on 2 are all kilogram meters squared per second. So that's our unit there. That's the information we've got. We've got the right-hand side of our equation. Now on the left-hand side we need to know the uncertainty in the momentum, because we're trying to find the uncertainty in the position. So the uncertainty in the momentum, delta P, is going to be m delta V. That's because the mass is not changing, it's the mass of the electron. But we know the uncertainty in the velocity because we were told that it was 1 by 10 to the minus 10 meters per second. So our uncertainty in the velocity is very tiny. We know within, what's 10 to the minus 10? 1/10,000,000th of a meter per second, how fast it's going. So we know very precisely its velocity, and therefore very precisely its momentum. So delta P is going to be 9.1 by 10 to the minus 31, which is the mass of the electron, times this uncertainty in the velocity, which is 1 by 10 to the minus 10, is going to give us 9.1 by 10 to the minus 41, is the uncertainty in the momentum overall, right? So now we've got everything we need. We can rearrange our equation. Delta x equals h bar on 2 divided by delta P. Right, we've just made delta x the subject, equals, we did h bar on 2 over to the right here, 5.28 by 10 to the minus 35. We know that delta P, because we just worked it out immediately above, is 9.1 by 10 to the minus 41. So that's a very tiny uncertainty in the position. And it turns out that our uncertainty, in the momentum, our uncertainty in the position, delta x, is going to be 5.8 by 10 to the 5 meters. That's 580 kilometers. So if we know the position, the momentum very precisely, we can't know the position precisely at all. If you have an electron within a range of 580 kilometers or kilometers, depending what you prefer, obviously you know nothing really about its position at all. So this is the uncertainty principle in action. Basically, we can know one thing extremely precisely and the other thing almost not at all, or we can know both of them reasonably precisely. It's an overall limit on the level of uncertainty, and remember that there was a greater than or equal to in the equation that I've been kind of ignoring on the way through. So that's the minimum uncertainty we can have. The uncertainty may actually be even greater than that.